Okay, we're back, and this time we're taking a look at some vectors, and instead of adding them together like you would have to do to find, say, a net force, a total force, if you have multiple vectors, this is something where if you have two different types of vectors, there are times in different quantities where we have to multiply the vectors together. So, okay, I suppose that's all fine and well, but what's kind of weird about this is there are two ways that you can multiply. That's a little bit weird. We're not used to that in normal arithmetic. One of the two ways is something called a dot product. More commonly known as dot product, but actually called a scalar product. That's because the answer that you get is just a number. It's a scalar. The second way is when you multiply two vectors and you actually get a third vector, which is a cross product. The cross product is especially strange because this third vector that pops out is actually perpendicular to the two vectors that you multiply. Okay, the plane that they form. Vector C in this case is going to be perpendicular to the plane of vectors A and B. So what I wanted this video to do is just kind of show you the mechanics of the machinery that you use to get the answers out. How do you actually do the multiplications? Let's start off with probably the easier of the two, which is the dot product. So I just made up two vectors here, and if you have a problem where you actually know the x, y, and z components of your two vectors, the way that you can go about trying to find the dot product. Now the name dot product comes about because of the notation that you have. You use that dot symbol for the multiplication. If you know the two vector components, the general formula is you take the two x components of your two vectors, multiply those, then you add the product of the two y components, and the same thing if they happen to have three-dimensional z components, you multiply those two together of your two vectors. So in this case, if this is what we're given in a problem, this is the version of the dot product that we'd want to use. So here we have two x components, 3 times negative 2. Now there is no y component of vector A, so 0 times 3, and then 4 times negative 6. And as you can see, this is just going to spit out some number. We have negative 6 plus a negative 24. And so the dot product, okay, the scalar product of A dot B in this case is negative 30. So, yeah, now this is just kind of a cute little math problem. That's all fine and good. Does this actually mean anything? Well, in real life, in mechanics, for example, the primary dot product that we're going to have is actually a little thing called work. Work is what we get if you have a force vector, which is being applied to some object, and if it actually moves the thing so that it has a displacement vector, work is technically the dot product of force and displacement. So in this case, if, let's say we change the names of these two vectors that we're given. Maybe our force vector was vector A, and maybe our displacement vector was vector B. And if we had those two components, check it out. This answer suddenly would be in units of newtons times meters, which is energy, that's joules. So you can actually find how much work is being done by those two particular, by that force moving some object. Now the good news is you don't have to use this version of the dot product very often. The reason for that is in most problems that we get in physics, you usually aren't given the actual vector components of two vectors. Instead, we might be told something like, or have a picture. Probably a real common example is, you're pulling on a box. Maybe there's a string attached or something, so you pull on the thing with, I don't know, maybe a force of 50 newtons. And the motion is only sideways. Okay, maybe you're pulling at something like a 30-degree angle. And your displacement that the box slides, let's say that's 2 meters. Okay, whatever the numbers happen to be. And the problem is you want to find out how much work is being done by that force to move that box. Well, we don't have the x, y, and z components of these two vectors. I suppose from this picture we could actually figure it out. But it turns out that the version of a dot product that we normally use, let me write it down generically here, is you take the magnitudes of your two vectors, if you happen to know them. And this is our vector notation for magnitudes with kind of like the absolute value symbol. And then what you do is you multiply it by the cosine of the angle between those two vectors. So again, if you had kind of like a vector A and a vector B, and there's some angle between the two, this is the version that we use more often than not. This is the version that we could use in a problem like this, where we're saying the work is the dot product of force and displacement. Well, the magnitude of our force is the 50 newtons. The magnitude of displacement is 2 meters. And there's a 30-degree angle between the two. Now, if you think about this, check out, say, the 50 Newton force times the cosine of 30 degrees. What does that represent? What is that on this picture up here? Let me change colors. That represents the sideways component, the x component of that force. There's also a y component that's pulling up on the box. But there's no displacement up. That y component isn't doing any work. Only that sideways portion is doing the work, and 50 times cosine of 30 would give you that x component. That's the cool thing about this way of doing a dot product. You kind of see geometrically what it means. You're multiplying the two parallel parts, the two parallel components of your two vectors. The answer that you get is just some number, and in this case that would be the number of joules that is being applied to move that box. Okay, so we've got two ways of doing dot products. The second way that I have here is what you'll use most of the time. Okay, and work, in our case, in mechanics at least, is the primary example that we have for dot products. Let's just go ahead and get to the trickier of the two, and that's going to be the cross product. This I'm just going to plow through because it's kind of weird and we just need to get the machinery under our belts. If you haven't done cross products, this is going to look awfully odd. Oops. Yeah, let me change that. We're going to set up a 3x3 determinant. Now this is something that you normally do in Algebra 2 in your math classes. It's probably easier just to go ahead and put some numbers in there. Just remind ourselves how to do this determinant. And might as well use the two vectors up here that we had before. So let's do force cross D, force cross displacement. Okay, so what this means is we have to put the x, y, and z components in of our first vector. notice I have these unit vectors, I, j, k, or x, y, and z components, kind of are placeholders there. Look at the first vector, 3, 0, 4. There's no y components, we put a 0 there. Z component's 4. The second vector is -2, 3, -6. Okay, so I just put those x, y, and z components in there. Now, to evaluate this thing, we have to expand it. Okay, so what you learn when you do matrices and determinants and all that is that the goal is to try to get it to a 2 by 2. Okay, so if you recall, what you do with this stuff is you multiply these, looking at these diagonal entries of the determinant, and it's AD minus B times C. Okay, so what you do, again, let's use a different color here. Let's say we want to find the x component of our new vector. Well, in this 3 by 3, the trick is you kind of cross out the column and row of I, and whatever's left gives you a 2 by 2 determinant. Then you have this weird thing that happens when you do matrices and all that, is you alternate pluses and minuses. So now the y component of our cross product cross out the row and column there, and what you have left is 3, 4, -2, -6. Then you alternate and do a plus for the z component. Oops. Cross those out, and what you're left with is 3, 0, -2, and 3. Okay. Now we use this 2 by 2 rule, and we can start getting some answers out. Okay, so for our z component, we have 0 times -6 is 0, 3 times 4 is 12, but we've got that minus sign there, so -12. Oops. 3 times -6 is -18, minus -2 times 4 is a -8. And our z component, 3 times 3 is 9, -2 times 0 is 0. And we're going to have an answer here. -12 is your x component. -18 plus 8 is a -10, but we have that minus sign, so it's plus 10j. And the z component is 9. Believe it or not, if you could set this up somehow in 3 dimensions, this vector that we just found, this cross product, would be perpendicular to the plane formed by these vectors up here. It's really bizarre. If you're talking about a force and kind of a displacement or radial vector, this would actually be torque. When we get to rotational motion, torque is going to be a cross product vector. Angular momentum is going to be a cross product vector. Next year in Chem Phys at least, when we do electricity and magnetism, magnetic force is going to be the cross product of velocity and magnetic field vectors, for example. So these cross products are going to come into play as well. Very weird. This is a strange kind of thing. This is the setup that we have to use and the machinery that we use to get an answer. Dot products, you get a scalar for an answer. There's 2 ways of doing those, depending what you're given in the problem. Okay, so this is all stuff that we have to kind of keep in the back of our minds and we'll use on occasion. Okay, so I hope this helps, and until next time, we'll see you later.